Hello, calculus fans. Let's find the mass and center of mass of a triangular lamina. It will have vertices 0, 0, 1, 0, and 0, 2. And let's suppose that the mass density function is rho of xy equals 1 plus 3x plus y. That's a measure of the mass density at any particular place. Here's a picture, and I've also marked where the center of mass is going to end up. So our formula for the mass of the lamina is the double integral of the mass density function. So we can set this up as an iterated integral. That's the integral from 0 to 1 of the integral from 0 to 2 minus 2x of 1 plus 3x plus y dy dx. You notice that upper bounding curve, y equals 2 minus 2x, that's actually something you have to work out knowing what the points are that make up that line. Okay, so we integrate with respect to y. We get this expression. If you plug everything in, and I'm sparing you all of the algebraic manipulations, you get 4 minus 4x squared, and now that has to get integrated from 0 to 1. That's pretty easy. You end up with 8/3. You should just double check to make sure everything works out here. Next thing we want to do is compute the center of mass. That means we have to compute x bar and y bar. So x bar is 1 over the mass times the double integral of x times the mass density function. So we'll put a 3/8 out in front. That's because that's the reciprocal of the mass. The limits of integration are the same because we're not changing the region of integration. And now what's different is we have to take the mass density function and multiply by x. That's going to make a difference when we compute antiderivatives. So we'll anti-differentiate with respect to y, plug in the y values. Again, I'm going to spare you the gory details of the algebra. You should end up with something that looks like this. 3/2 times the integral from 0 to 1 of x minus x cubed. Work all that out and you'll get 3/8. Next thing to do is compute y bar. Same setup. We have 1 over m out in front. The region of integration is the same. Now we take the mass density function and multiply by y. Anti-differentiate, and then we'll plug in the 0 and the 2 minus 2x. This is really going to get algebraically messy. And again, I'm sparing you all the algebraic manipulations, but this is what we get. And if you work all that out, you get 11 over 16. So this is the y coordinate of the center of mass. Therefore, the center of mass is at the point 3/8, 11/16. And we've redrawn the picture and marked on here the coordinates of the center of mass of this thing. Okay, that's all for now.